Okay, welcome back to lecture 19.3, where I want to mention a little bit more about phase transitions before going on to think about the third law of thermodynamics. So last time we talked about the heat capacity of solids, the heat capacity of metals, and the heat capacity of superconductors. So you haven't learned any of this yet, but I kind of want to talk about what happens to metals. So actually, if you look at the phase diagram, the periodic table, actually most of the metals in the periodic table at low temperatures become superconductors. There's a few that don't, and they're actually kind of unusual ones. I'll mention them: copper, silver, gold, platinum. These four, and also the magnetic ones, iron, cobalt, nickel, do not transition. Okay, so the magnetic ones are kind of unusual. Actually, there's something that these other metals have in common. We can talk more about in class. But most metals become superconductors at low temperatures. I told you last time that the heat capacity of a metal, the electrons in a metal, was proportional to T. So if we look at the entropy, right, that we had, we should have something that went like the integral of the heat capacity. So let's do dq over T. We go from T0 to Tf. So we're going to replace that with the heat capacity C dt over T. And let's imagine we're going to do the heat capacity of a metal. So we're going to go from T0 to Tf. So we're going to replace this with let's just say it's some constant. I don't care what it is. Some big A times T dt over T. Then you can see that our heat, these would cancel. We would get T0 over Tf. Our constant would come out of dt, and this would be A T evaluated from T0 to Tf. And so let's just write that as A times Tf minus T0. So this is our delta S, but what is the entropy of the final state, right? Well, that's just A times Tf. Right? That's just remember, our entropy is extensive. We can just add it and subtract it. So if Tf goes to 0, then our entropy goes to 0. So this should satisfy the fact that we no longer have that singularity like we did for an ideal gas. So this should be okay, but in fact, most metals actually transition into superconductors with that exponential e to the minus delta over T, some faster temperature dependence. So in fact, nature seems to prefer that things transition that systems transition from those with large entropy to those with small entropy. Or another way to think of it is, so heat capacities that were constant are not okay at low temperatures. And in fact, what nature really wants is your heat capacity to go to zero as T goes to zero, so that your entropy can go to zero. So these are called, when I transition from one state to another, this is called a phase transition. And there's actually two kinds of phase transitions. There's so-called first order phase transitions and second order. So the original classification of first order and second order phase transitions came from Ehrenfest, and he talked about how first order phase transitions involved a discontinuity in a first order variable. We'll talk more about that later. And second order phase transitions didn't have a discontinuity. But nowadays we actually generally classify first order phase transitions as those that have a latent heat. We've already talked about latent heat a little bit. For example, when we go from water to ice. We talked about cooling down some water and freezing it, and there's a latent heat of fusion. Fusion just means solidification here, right? So for water, this is 3.35 times 10 to the 5 joules. 3.35 times 10 to the 5 joules per kilogram Kelvin. Remember, we talked about that when we talked about our heat pump example. Now, when we go from a liquid to a gas, or from a gas to a liquid, there's the so-called the latent heat of vaporization. LV. For water, that's so this is, imagine going from water to steam or back again. LV was 2.25 times 10 to the 6. 2.25 times 10 to the 6 joules per kilogram Kelvin. So really it takes a lot of heat to vaporize water. To go from the, what's this for water? So it takes a lot of heat for it to transform from liquid to gas. So we're going to do an example in class where we're going to freeze a tray of ice cubes. Freeze ice cubes and calculate the entropy that's associated with that freezing, right? Because remember that to do this, we have a certain amount of heat, which we're going to have to put in, which is going to be m times the latent heat, right? So the mass times the latent heat is going to give you how much heat you have to put in to freeze it, to vaporize it, or how much you would have to take out to liquefy it or to freeze it. So we're going to do an example in class where we do that. So, but it's really quite interesting. Not only does our system want to go towards very low entropies at low temperatures, but also we want to seem to have phase transitions where we take out even more entropy as we cool down. Okay, so this is a really interesting thing we're starting to see And we're going to explore that in the last part of this lecture on the third law of thermodynamics.